Alright, now we're going to focus on one form of matter right off the bat here, and that's going to be the atom. And we're going to talk about what makes an atom up and what defines an atom. Atoms are made of three primary subatomic particles: the electron, the proton, and the neutron. These subatomic particles are differentiated on the basis of two factors: mass and charge. Alright, the first subatomic particle we want to talk about is the electron. The electron is said to have negligible mass. Notice we did not say, we use the term negligible mass, not no mass. Electrons do have mass. However, their mass is so small compared to the mass of the proton and the neutron, that when you add the mass of the electron to the mass of the proton, you get the mass of the proton back, because the mass of the electron is so small compared to the mass of the proton. So we say electrons have a negligible mass when it comes to determine the weight of an atom, or the mass of an atom. We say that electrons have a relative charge of -1. Before the end of this semester, we'll actually define in terms of coulombs what the charge of an electron is. But for talking purposes, for conceptual purposes, we always refer to an electron as having a charge of -1. The proton is almost the bizarro evil twin of an electron. It has a mass of 1 AMU and a relative charge of +1. So what we mean is that a proton has a charge equal in magnitude but opposite in sign to that of an electron. We say that a proton has a mass of 1 AMU. Well, what's an AMU? An AMU stands for atomic mass unit, and the atomic mass unit is defined as 1/12 the mass of a carbon-12 atom. However, you don't need to know that. What you need to know is that an atomic mass unit is a unit of mass made up by chemists for the sole purpose of giving a proton a mass of 1 AMU. Our final subatomic particle that we want to talk about is the neutron. The neutron is a political moderate. It wants to be taken seriously and given all the weight of other politicians, but it's scared to take a stand. So a neutron has a mass roughly equal to that of a proton, a mass of 1 AMU. However, it has no charge. This also brings up one of my favorite jokes. A neutron walks into a bar where the proton's a bartender. The neutron asks, "How much for a drink?" The proton says, "For you, no charge!" The neutron says, "Are you sure?" The proton says, "Why, yes, I'm positive!" Make sure you try the salad bar. I'll be here all week. One last thing I do want to point out is, remember how I said that the proton has significantly more mass than that of an electron? A proton's mass is about 2,000 times the mass of an electron. That's why when we're calculating the mass of an atom, we really only look at the protons and neutrons and ignore the electron's contribution. All right. Write down the word Aiden. A-I-D-A-N. Write down the word Aiden. A-I-D-A-N. Aiden. It's a name, right? Once you've written down the word Aiden, let's talk about electrons. The electron was discovered by J.J. Thomson. He discovered electrons while playing with a cathode ray tube. This picture shows a picture of a cathode ray tube, and I actually have a video either posted, if I'm lucky, edited into this lecture. If I'm unlucky, it's posted at the end here, of a cathode ray tube. A cathode ray tube consists of two metal plates These two metal plates are placed in a vacuum tube. What do I mean by a vacuum tube? I mean that all the air has been removed from this tube. Instead, a phosphorescent screen has been placed in there. In other words, something that's going to show green when a cathode ray hits it. The cathode ray tube is then hooked up to a power source. The negative end of this power source is the metal plate known as the cathode. The positive end of the electrical source is attached to the metal plate known as the anode. When a charge is run through the tube, a stream of particles is emitted from the cathode and travels to the anode. So particles leave here and go to here. Because these particles leave the negative electrode, or the cathode, the particles are referred to as cathode rays. Thomson did not invent the cathode ray tube. He was simply playing with it and made some useful observations about it that led to the discovery of the electron. What Thomson noticed was a couple of things. First, Thomson noticed that it didn't matter what he made the electrodes of. No matter what he made these electrodes of, he always saw cathode rays produced, and those cathode rays always flowed from the cathode to the anode. That let him conclude a couple important things. He tried several different materials to make these cathodes from, and no matter what material he used, he always saw the cathode rays flowing from the cathode to the anode. That led him to conclude two things from that observation. First, all substances had to include these cathode rays. Also, if the cathode rays always went from the negative to the positive, the cathode rays had to have a negative charge. Why? Well, they're flowing towards the positive charge, right? And opposites attract. So if something's flowing towards the positive charge, it itself must have a negative charge. So those are two important observations Thomson made. The next observation was really awesome and allowed him to do some math. He decided to place a magnetic field next to his cathode ray tube. When he placed a magnetic field to that next to that cathode ray, he noticed that the cathode rays were deflected. He placed one end of the magnet near the cathode rays, and the cathode rays would actually bend towards the magnet. If he then flipped the magnet over and used the other side of the magnet, the electrons were actually repulsed by it, or the cathode rays. And yes, of course, I kind of let the cat out of the bags numerous times here. This cathode ray is actually a stream of electrons. So he discovered that these stream of electrons definitely had a charge because they were responding to the presence of a magnetic field. They did the same thing in the presence of an electrical field. Now, the reason this was important was it was well known at the time the relationship between charge, mass, and force. So what Thomson did was he took electrical plates, placed them on the side of this cathode ray tube here, and he turned on these electrical plates to a certain voltage. He then measured the degree to which he was deflecting the electrons as a function of the potential of the electrical field. That allowed him, since he was essentially knew how much force he was applying, he knew the mass to, he was able to calculate the mass to charge ratio that these particles or these electrons had to have. So Thomson was able to calculate So by using that electrical field and measuring deflection, Thomson was able to calculate the mass to charge ratio of electrons. However, he was never able to either calculate the charge by itself of the electrons or the mass of itself by the electrons. Therefore, he hit kind of a roadblock. He knew that electrons existed, he knew that all materials contained them, and he was even able to determine their mass to charge ratio. But he couldn't break the ratio deadlock. He couldn't determine either the charge or the mass. That was done by another chemist named Millikan. Before we look at Millikan's work, real quickly summarizing what Thomson did, he observed three things. Cathode rays always flowed from cathode to anode. Cathode rays are deflected by negative electrodes. The property of a cathode rays were independent of the material from which he made the electrodes. So he was able to conclude that cathode rays had a negative charge and that all matter must contain these negatively charged particles. He was also able to calculate the mass to charge ratio, but never them separately. Millikan designed a very simple but elegant experiment to unravel the mass to charge ratio of an electron that Thomson had calculated. What Millikan did was he used an aspirator to generate really, really small oil drops. Matter of fact, let's look at this on a bigger picture here. He used an aspirator to generate really, really small oil drops. He then allowed these oil drops to fall until they reached terminal velocity. Why this is important is because that helped him calculate the mass of these oil drops that he was creating. What he then did was he then shot X-rays at these oil drops. What these X-rays did was they kicked electrons off the oil drop. So I've got my oil drop here. I'm falling at a terminal velocity. So Millikan's able to calculate my mass here. Millikan comes along and says, "I'm shooting you with X-rays." Oh no! And when the oil drops are hit by an X-ray, they lost an electron or multiple electrons. That left the oil drop with a positive charge. These positively charged oil drops are then falling between two charged plates. Using observation of the human eye, he would manipulate the charge on the two plates until the charge of the two plates was enough to counteract the falling of the drop and freeze the drop in midair. Because he knew the voltage between the two plates, and he knew the force due to the pull of gravity on each drop, he was able to calculate what the charge on each drop was. So his experimental design was brilliant, but what he did next I think was even more awesome. Now, what Milken couldn't control with his experiment was how many electrons were lost by each drop. He could just calculate the charge in the drops. Some drops would lose 2 electrons, some drops would lose 3 electrons, some 4, some 5, some 6. So what Milken did was he took the charges in all the drops and he subtracted the charges from one drop to this front. He subtracted the difference in charges between all the drops. And he found the smallest difference that he found between any drops. And he assumed that that was the charge of an electron. Then to test it, he divided the charges in all those drops by that smallest difference. And if that was truly the charge of an electron, then all those charges he should be seeing should be whole number multiples of that smallest amount, which they were, and thus became the charge on the electron. And he discovered that the charge of an electron, according to his measurements, was 1.59 times 10 to the negative 19th coulombs. Further scientific work with more advanced equipment has come up with a current accepted value of 1.602 times 10 to the negative 19th coulombs for the charge of your electron. Why don't you write down Sally? Write down the word Sally. Sally Malik. You don't need to write down Malik, but write down Sally. S-A-L-L-Y. That's it.